All right, so this is the lecture for November 22nd, the Monday-Wednesday class, class before Thanksgiving. All right, so we're going to continue on polymers. I wanted to go over the crystal structures that we typically see with polymer systems. So we talked about the MERS, which are the at least two carbons and the respective side groups that create a polymer. And this would be a kind of example of how they would line up to create crystals. So the polyethylene material, two carbons, four hydrogens, repeats over and over again, has a very straightforward, fairly straight chain of carbons that line up in kind of a zigzag pattern. The fact that the very small side groups, the hydrogen, can interact with other hydrogen groups pretty closely, and these chains will fold over and pack very closely together. So this would be, say, one chain folding over and over again, creating a fairly compact amount of atoms within a volume or of the crystal. So we would have the number of repeat units. In this case, it may be several thousand, packed in a very crystalline formation. Okay? And as we talked about yesterday, if it's more of a amorphous, tangled position, then the same amount of polymer would take up a much larger space, and the density therefore would be much lower. Okay, so this is another example of how it would look like at a larger view. The chains of polymer fold over each other, creating these rows, and they usually are set length determined by the size of the material that we're polymerizing, and then it'll fold back over itself and create columns and go back and forth, creating a crystalline, fairly well packed crystal structure. Okay, but the amorphous components do exist outside of these crystal structures fairly easily, so it's very difficult to get really high crystalline polymers. 100% is essentially impossible. There are going to be segments that are not well crystallized, but the sections that are follow these very nice repeating rows and column patterns. Okay, so getting into this is why can certain polymers crystallize very well and other ones can't. It really comes down to isomerism. So we'll use C8H18 as an example. So that means that there are 8 carbons along the backbone, and then the 18 hydrogens that connect them. So this is a polyethylene material with 4 mer units. Okay, but C8, 8 is octa in Latin, so this is actually octane, which most of you should know is gasoline. So this is the structure of gasoline. It has the 8 carbons and the respective hydrogens. But isomerism means that we can have the same molecular structure, C8H18, but we can arrange it in a different formation, and it'll make a completely different material with completely different properties, as well as strengths and crystallization properties. Okay, so this is the most simple version. If we continued the carbon backbone to, say, several thousand of them, we would no longer have octane, we would have a polyethylene. But this is an example of what you can do with the same crystal structure. This is also, not crystal structure, but the same polymer structure. This is also C8H18, but the backbone, which is the main unit of carbon-carbon bonding, is actually a 5 carbons, or pentane. We attach one of the carbons with its hydrogens, or a methyl group, on the second carbon. So we call that 2-methyl. And then the 4th carbon over, we attach an ethyl group, 2 carbons and its respective hydrogens. So this is still C8H18, but it does not have the same properties as octane. It has 2 large side groups, and if we continued this polymer with this repeat unit over and over again, if we tried to crystallize this material, it would be very difficult because the side groups would get in the way. So this would be more of an amorphous material that would have much different properties than if we kept the orientation just carbons and hydrogens in the same chain. Okay, so that's an example there. All right, so let's go over the main polymer types that you'll need to know in this class. So again, we're talking about MER units here, the simplest repeating structure. The MER is also the repeat unit, same thing. And there are about 10 of them that you'll need to know. And these are the first 5, and they're fairly simple. First one again is polyethylene. We've talked about that a fair amount. And we can determine the atomic weight of this MER. So A sub W for atomic weight, just like we did the atomic weight off the periodic table for ceramics and metals. For the MER, we just add up all of the atoms that make up the MER unit, and we add those together to get the atomic weight. So in this case, 1 MER unit would have 2 carbons, 4 hydrogens. Carbon has an atomic weight of 12 off the periodic table. Hydrogen has 1. So we'd multiply our 12 times the 2 carbons and our 1 times the 4 carbons, and we get an atomic weight of 28, right? 24 plus 4, that would be in grams per mole. This is the atomic weight of polyethylene MER unit. Okay. The next one is a modification of polyethylene. We have the 2 carbons, we have 3 hydrogens, and 1 hydrogen has been replaced with chlorine. Chlorine is a very big anion atom, which we learned about in ceramics. It's hanging off of the side here, which does affect its polymerization and its crystallization properties. But again, we would add up the 2 carbons. In this case, 3 hydrogens and 1 chlorine. Add those up, and it'll give us our atomic weight. Okay, the third one here is polytetrafluoroethylene, or Teflon. This is the material that the speakers from Gore talked about. This is the fluorine material that is used in pretty much all the components sold at W.O. Gore and Associates. I'd say 98% of their products include this material. And what's so nice about it is it's very inert. So the fluorine to carbon connection is so strong that nothing else really interacts with this polymer. Therefore, it's great for coatings, on pots and pans in your kitchen to keep stuff from sticking, and great for vascular grafts to keep blood flow from attaching to the walls of the vessels. So this is a very inert material. Okay. Again, its atomic weight would be 2 carbons and 4 fluorine. Okay, we'd add those together. Okay, polypropylene, this is the water bottles that most students bring to class, the ones with the fairly thick wall, somewhat transparent. You can use over and over again. This is polypropylene. Again, it's the 2 carbons, 3 hydrogens, and then the 4th hydrogen has been replaced with a methyl group. This group again is fairly large, so it hangs off as a side group, making the material. Still, you can crystallize it, but it's going to be not as easy to crystallize as polyethylene. Okay, and the last one we have on here is polystyrene, 2 carbons, 3 hydrogens, and then a phenol group. The phenol, this is the hexagon aromatic ring that we talked about as one of the side groups that you would need to know about. So let's figure out the atomic weight of these two. So this first one here, polypropylene, we have 1, 2, 3 carbons, and we have 1, 2, 3, and then H3 is 6 hydrogens. So we add that up, we have 12 times 3 plus 1 times 6, and I get, let's see, 36 plus 6, that would be 42 grams per mole. Okay, that would be the atomic weight of polypropylene. And then this last one, let's see if we can get this one. How many carbons do we have? We have 1, 2, and then the aromatic ring or the phenol group has 6, so that would be 8 carbons. Then there's 1, 2, 3 hydrogens on the main group, but there's also hydrogens hanging off of the extra attachment of the phenol group. There's only 5 out of the 6 because the 6th carbon is attached to another carbon. So that would be 5 plus 3. There's also 8 hydrogens. So 8 carbons, 12 times 8, if I remember right, is 96, I think. 84, 90, let's see, 84 is, yeah, 96. And then 1 times 8 give us 8, So the atomic weight of polystyrene is 104 grams per mole. Okay, so just from this, if the polymers have the same number of repeat units, the polystyrene is 4 times the weight, grams per mole, of polyethylene. However, with this big side group on the side, it's a lot harder to crystallize this material. Therefore, we can't pack in the chains of polystyrene as closely as we could polyethylene. Therefore, most likely the density is going to be fairly similar, because even though you can probably pack polyethylene about 4 times more densely than you could polystyrene, but then the polystyrene is 4 times heavier, so you get kind of a balance in the densities. So usually polymers have a density of about 0.5 grams per milliliter up to a max of about 2 to 3 grams per milliliter. And this is all based on the weight of the mer and the amount of crystallinity you can create. Okay. All right, so this is an actual atomic model of one of the polymers we just talked about. Let me erase my notes on here. Trying to erase them. There we go. Just so you can see the structure a little bit better. So this is one of the 5 I just talked about: polyethylene, polypropylene, polystyrene, polytetrafluoroethylene, or polyvinyl chloride. Which one is it? So let's take a look at this. So the large gray atoms are the carbons. So this is our carbon-carbon chain that makes up the base unit. The small atoms are the hydrogens. So there's only the 2 types. There's only carbon and hydrogen, so that kind of gets rid of the Teflon and the vinyl chloride, because there's no chlorine or fluorine atoms. So it has to be one of the top 3 here. If you look at it, these are the side groups: hydrogen, hydrogen, hydrogen. So we'll show this. This is one of the mers. The 4th group is that hexagon ring. Okay, 6 carbons, and it has the 5 hydrogens. The 6th carbon is attached to another carbon. So that would be the polystyrene. So this is what polystyrene would look like. Again, if I fold over a polystyrene ring, I have to fold it way over here and come over in this direction. And I have to be far enough away so that the side groups have room to so they don't interact too closely. So the fact that they're very spaced out means it's very hard to crystallize styrene. And as you might know, polystyrene is also styrofoam. Styrofoam obviously is not see-through, but that's because they blow the styrene full of air bubbles, and that makes it opaque. But polystyrene in its natural form is extremely clear, and it would be it's the material that is used for CD cases, for music CDs, and a lot of packaging, especially around the holidays. A lot of the hard, clear plastic packaging is usually polystyrene because it's very clear and shiny and looks good, but very brittle material. You know, if you bend a CD case, it'll almost shatter on you, almost like glass. So that's because it's very amorphous and it's hard to crystallize. But it is a pretty strong material because of this side group, and the chain is pretty strong, so it makes a strong material. Okay, so those are the main 5. Here's the next 5 that you should know. These are a lot more complex, obviously. These are the mers for each one of these materials. So I would put my parentheses around here, put my N next to it. That would mean that I can repeat this as many times as I want. As you can see, the complexity goes up dramatically. Okay, so this first one is called polymethyl methacrylate. This is highly used in biomedical uses. It's in smaller repeat units, so the N value is maybe 100 or so. It makes a really good glue material, kind of like a super glue, and it's used quite often to fix implants into the body, especially hip implants into the bone. They'll use PMMA to glue the implant into the bone and get a better healing response. It's also used for contact lenses. Since it's a very clear material, the fact that it has this big side group hanging off the side makes it hard to crystallize, but it makes a very optically clear material, and it's really good for the hard contact lenses, not the soft ones, but the hard ones. Those are made of PMMA. But if you look at it, it's really a combination of polyethylene, the hydrogens, polypropylene, a methyl group, and then the last hydrogen has an aldehyde, the double bonded oxygen, an ester or an ether, names are used synonymously, a carbon-oxygen carbon bond, and another methyl group at the end. So very large dangling kind of piece coming off the side of PMMA. So what would be the atoms that are associated with this MER unit? So we have carbon, hydrogen, and oxygen. So how many carbons do we have? We have 1, 2, 3, 4, 5. How many hydrogens? 1, 2, plus 3 more, 5, plus 3 more to that is 8. And then oxygens, 1, 2. So we'd add up all of those and we could get the atomic weight of polymethyl methacrylate. The next one is bakelite. It's not used as much anymore, but this is an interesting structure because it's a hexagon that's attached to other hexagons by 3 different positions. So this is a unique material because it's what we call cross-linked. It's not just one chain that continues in one direction. It cross-links in 3 dimensions, or at least in 2 dimensions. This is kind of a one-dimensional polymer. This is a 2-dimensional polymer. Most of these are, as you'll see down here, are also one-dimensional. So this is a special form of polymer, and we'll talk about it later. But it interacts really well with other components, therefore it's hard to change its shape. It doesn't crystallize very well, and it can't because the chains aren't long enough to fold over on themselves like the one above it. It's already interconnected. So it's actually a really strong polymer. It's very hard to melt, and it's very brittle, mainly because I can't pull it without stretching all the bonds. These bonds here stretch almost instantaneously. So the material acts a lot like a ceramic. If you pull it a little bit, it resists dramatically and then it breaks. Whereas these materials, since they're very amorphous and they get tangled up and they're nice long chains, we could pull them apart for a while before they actually interact. Okay, so let's look at this next one here. This is the nylon polymer, or basically nylon rope. As you see, it's quite complex. It has nitrogen in the backbone, carbons, oxygens, and hydrogens. So this is how you would draw out the kind of short version of the MER, but when you break it down, you'll see quickly there's a lot of atoms in this MER. Okay, so there's carbon, hydrogen, and oxygen, just like in the top one, polymethyl methacrylate, and even in bakelite. How many of them are there here? So we have a carbon here, a carbon here. We have carbon here, but this tells us that there's actually 6. So this is kind of a polyethylene with 6 carbons. We have another one over here that has 4. 4 carbons with 2 hydrogens each, so kind of a polyethylene type material as well. So how many actual carbons are there? There's 1, 2, plus 6 is 8, plus another 4 is 12. Okay, and then how many hydrogens? 6 times 2, 12. 4 times 2 is 8, 12 plus 8 is 20, 21, 22. And how many oxygens? There's only the 2 oxygens. Okay, so add all those up, I would get the atomic weight of a MER of nylon. The next one is PET, which is a form of what's called a polyester. Polyester means it has many ester groups in it, so it has a lot of oxygens combined with carbons along its backbone. Also has a phenol group in here. And the phenol group really distorts this polymer. It causes the backbone to bend in a really weird shape, kind of like a chair shape, so we don't get a nice straight polymer. And that again makes it very difficult to crystallize, since the shape is not nice and straight. Even though there aren't really big side groups hanging off of this one, the shape doesn't allow it to crystallize very well. So PET is a very clear material, but this, and this make the material actually quite strong. And this is used in disposable water bottles. So I have a disposable water bottle here, and you can hear it's the ones that are really crunchy. So they're very thin, very clear. You buy these water bottles, and the material is very kind of hard and crunchy. Why they use it is because if you weighed this water bottle, it weighs less than a gram. So using a tiny bit of polymer versus a polypropylene bottle would weigh probably 4 or 5 times more, and it's much thicker. They get a very similar strength out of PET, use a lot less of it. So it's very inexpensive, and it's clear, so it makes a nice bottle for water. Alright, and then the last one is polycarbonate. Polycarbonate, as you probably know, is used for kind of replace glass windows. Plexiglass is a type of polycarbonate that you may have heard of. They use it for like aquariums and things like that, especially the larger ones. But polycarbonate is even stronger than plexiglass, so you can use less of it. And if you use about half an inch to an inch of polycarbonate, it becomes bulletproof. So a very strong material. And again, it's the ester, the phenol groups that really improve the strength. But again, these shapes really distort the shape of the polymer, so it has a very distorted backbone. So if you try to crystallize it, it's pretty much impossible. That's why polycarbonate is so clear, and it's also why it's so useful as a replacement for glass, a bulletproof replacement for glass, if you need that. Hopefully you don't. So again, if you wanted to calculate the atomic weight of this, you'd have to add up all of these carbons, the carbons here, the carbon here, all the oxygens, there's at least 3 of them, hydrogens, and then you can calculate the atomic weight. Alright, so this is a mer that has 3, well, this is a polymer that has 3 mers. And wanted to ask you guys, which one do you think this is of the 5 we just talked about? So we'll look at it, the very distorted shape. This is the backbone here. Goes around. Very distorted. It's not straight. It has this kind of curved shape to it. Okay. And if we look closer, we'll see there's 2 phenol groups in the backbone. There's also these red ones are let's see, I believe it's oxygen, so they're showing oxygen is red. Most of them are in the backbone, and then there's this one here that's double bonded. It's sticking out from the side, a little bit hard to see, but it's sticking out. And then there's oxygen, so there's ester groups. There's an aldehyde group. There's a phenol group. And this would be the polycarbonate, PC, that we were talking about. So this shows you how stressed the backbone of polycarbonate is. Very hard to curve this around and try to make a material that can crystallize. You can't really line it up very well. If you go up this way, very hard to crystallize this material. Therefore, it's amorphous. Light goes through it and makes a very clear but strong polymer. Okay. So those are the 10 types that you need to know for this class. And how do we make them again? We talked a little bit about how you create polymers from the mers or from the monomers, creating the mers that repeat over and over again and make the polymer. There's 2 ways you need to know to make polymers. There's the addition reaction, which is what we highlighted already, and there's the condensation reaction. So addition reaction means that I can attach mers to mers without adding anything else. I don't have to add hydrogen, I don't have to add water, I don't have to make water, I don't have to release anything. Whereas condensation, I have to break something off of the monomer and then attach another monomer, and then the part that breaks off can attach to form some kind of condensate. So things like fluorine gas, which is very toxic, can be formed. Chlorine gas can be formed, but there could be much milder things like oxygen or water can be released. Okay, so depending on your application, if you can form the polymer before you use it, you can have a very toxic polymer during the formation, and then it'll be very inert when you use it. But a lot of times polymers can be formed inside of something, like inside the body. In that case, you wouldn't want your condensate to be anything damaging. You'd want it to be water or saline or something like that. Okay, so let's look at the two types. So let's see, this is in the wrong spot. Let me move this down. This is supposed to be down here. And then these are all part of the addition reaction. So I'll kind of try to circle it. Okay. So addition polymerization, we talked about this. You add a catalyst or a free radical. We talked about excuse me, benzoyl peroxide, which is a well-known catalyst. It comes in, it'll break the double bond in an ethylene. Ethylene is the monomer. It breaks this bond here, opens up a space on the side, on both sides really, because carbon has 4 sides. It attaches to it, leaves the side open. Another ethylene comes in. It reacts with the reactive site, breaks the bond, creates another one. And you don't have to add anything. The 4 hydrogens are already there. All you're doing is you're breaking the double bond. And in addition reactions, that's typically what you'll see, is you'll have to break a double bond to create the polymer. Doing that aren't required to add anything else or remove anything from the reaction. So as you see here, catalyst has been formed, reactive site, another ethylene comes in, breaks the bond, and it continues on, propagates. So as it continues to form, we call that propagation. When we add the radical or the catalyst, that's called initiation. And then when we add more radical at the end, we can add it again at the end, that will stop the reaction. That's called the termination step. Okay, so we have initiation, propagation, and termination. Okay. For condensation polymers, it's a little bit different. We have our monomers. In this case, they're the same, but they're just flipped, as you can kind of see here. The hydrogen, nitrogen, these are flipped, but they're the same monomer. You can have 2 different monomers coming together. We'll talk about that here in a minute. But what you're doing is you're removing some of the atoms that are bonded so that you can free up a space for them to attach. So if we remove the OH, which is an alcohol group, and the hydrogen from the other one, the carbon and the nitrogen will attach. And you see that right here. If you move over to this side, these have now bonded. And what was released was 2 H's and an O, which is water, H2O. Okay, so this is the condensate. We have to remove atoms from the monomers for the reaction to occur, causing that to be released. Again, if I add in something like O2 to create an initiation, that would also be this type of polymerization when you have to add other components. But when you release components, those are called condensates, and that's a condensation reaction. All right, so let's go into some of the terminology that you see for polymers. Okay, so we were talking about the fact that polyethylene has a nice kind of zigzag shape, very straight, whereas polycarbonate has a very bent shape, right? And it continues and bends in different directions. This is really called conformation. Conformation is the fact that the side groups that hang off of your backbone force the polymer chain to change shape, right? So if we just have little hydrogens here, they can exist in any region here outside the carbon. They don't really interact with the backbone, and they keep the backbone very straight. But if I put something big, like a big methyl group or a big phenol ring, something that hangs off, I'm going to force those atoms to try to stay as far away from each other as possible, because usually they have a similar charge. They will bend the backbone so that it takes an odd shape, right? So in this case, but what's not happening is we're not actually twisting the carbon bonds. We're not twisting them this way where we're rotating. We're just bending them. They were straight, and we're bending them down like this, carbon, carbon. The twisting motion would actually break the bond. Okay, so as we talk about different formulations, you can see that maybe the side group is up, straight up versus straight down. To rotate from up to down, you'd have to twist the bond and break it. Okay, so that would be a different polymer because you have reacted it to put the side group in a specific position. If you want to change that, you have to react the polymer and change the reaction to create the side group. You can't just twist it. Okay, but you can bend it, and that's what this is for. And when you bend the chain, the carbon-carbon or carbon-oxygen, whatever your backbone of the polymer is, that's called conformation. Okay, so besides conformation, there is stereoisomerism, and this is where you would only get the other version or the kind of the mirror image of the other polymer if you broke a bond, right? So if you see this version of this kind of an ethylene polymer with a side group attached. When we react it, we break that double bond. It's just one bond now. But we could make two versions of it, right? We could have the side group down, or we could have the side group go up. The problem is we can't rotate this bond without breaking it. So this has to be chemically formed. So if we're creating a chain that's propagating this way, and the side group is up, that is controlled by the chemical reaction versus a side group that's down. Okay, so since you have to twist to form this one, this is not conformation. This is stereoisomerism. Okay, and this is a way that chemists use to create similar but very different versions of the same polymer or anything else. And a good example is this is carbon, has four different side groups, A, B, D, and E. If I had a mirror here, I can kind of see a mirror image of itself where it's A, E, D, B. This is actually a very different configuration because I can't twist these side groups so that they become the polymer over here. This has to be chemically formed. Okay, so I'd have to break the bond to actually form this. So this is done quite a bit with, a good example would be sugar versus an artificial sweetener. Okay, so obviously these are quite popular in society because people want to reduce their sugar intake, so they try to have sodas and different things that have artificial sweeteners in them. A lot of people are concerned that artificial sweeteners aren't good for you, but a lot of people also say sugar is not good for you because if you don't use it, you just store it as fat, right? So what this is this is used, stereoisomerism is used to take a sugar molecule, which is one of those hexagon rings of carbon, has some oxygen and some alcohol as well, and they change the shape of the side groups. Okay, so they go in and they take a sugar and they say move this side group over to here. What happens is that's chemically modified. It still kind of tastes like sugar to your tongue, okay, but obviously everyone knows they have a little bit of an aftertaste, but different versions of these can taste still like sugar to the tongue. But what the body does is when this goes through the body, it doesn't recognize it. So the body is looking for, say, this configuration of sugar, and it sees this one instead. The body will actually ignore it. It won't break it down. It'll just go through your system and be excreted, and it doesn't get metabolized. It doesn't get stored as fat. Okay, so basically you're tricking your tongue here, but then you completely trick your body into not even seeing the sugar. So there's a lot of claims that artificial sweeteners are bad for you. Modifying this can cause variations in how it interacts with the body. So it's possible that artificial sweeteners could be bad for you, but there's really no evidence that artificial sweeteners are any worse for you than the original sugars that they come from. So there's a lot of claims of that, but when you look into the research, there's not a lot of data to back that up. Okay, so we have the ability to chemically put side groups on one side or the other, or randomly orient them differently. And again, if I want to move those, I'd have to break a bond, which means there's a stereoisomerism issue with that. And the way that I arrange the side groups is called tacticity, right? So if I go through and I purposely put all of the side groups on the same side, iso means same side, or iso means same, and tactic means the sides. So this is a same side version of this polymer. So this would be an isotactic polymer. So if R was chlorine, this would be polyvinyl chloride, and I can create a polyvinyl chloride that all the chlorines are on one side, and that would be an isotactic polyvinyl chloride, and it would have slightly different properties. What's another option? Well, if I went through and chemically alternated the side groups so they alternate in a repeating pattern, one side to the other. Again, these could be chlorines. This would also be polyvinyl chloride, but it would be a syndiotactic version. It would probably have different properties. It would have a different shape. The backbone would have a different shape than this one, because the chlorines would, bend this backbone into a weird shape, whereas this one, since they're distributed equally, would probably keep it fairly straight. So this would probably be a little bit easier to crystallize, whereas this one might not be. So that would really change its properties and its visual properties as well. So isotactic, syndiotactic, and then the last one, this is what we typically do. If you just take the polyvinyl chlorine monomers and you throw them in a vat and you add a catalyst and you let it go, you're probably going to get a very random distribution of the side groups. Okay, so this is called atactic, or kind of random displacement of side groups. And this would be kind of a general polyvinyl chloride. Again, if this is polyvinyl chloride, this would have slightly different properties than isotactic or syndiotactic polyvinyl chloride. Okay, and usually it comes down to how well you can crystallize it. All right, this is another one we see. We typically see this with double bonded polymer systems. So pretty strong bond. We have side groups. In this case, we have a methyl group, and we have hydrogen, and then we have the chain continuing inside of here. Okay, so as you'll see here, the side groups are both on the same side of the chain, right? Here's the carbon-carbon bond. They're on the same side of each other, both on this side. That's called cis, or same side. Okay, what that does is it forces the chain to have this kind of bumped shape, has like a little bumps in it, but it's still a fairly straight polymer. The other thing I could do is I can cross over the side groups. I could put one on one side, one on the other. When I do that, it forces the chain to take this stair-step shape, which again is going to change how I can crystallize it and the properties of the material. But if the side groups across a double bonded backbone, if it's across from each other, that's called trans, or across from. So this would be a trans polymer, this would be a cis polymer. Again, different properties, even though they're the same polymer with the same mers and the same carbon-hydrogen ratios. Okay, so now that we have an idea of the different kinds of polymers, we can take different polymers and attach them in different orientations to make what's called copolymers. Okay. Well, before we do that, let me do a top hat question. See if you guys can get this one. Obviously, this is recorded. This is more for your own understanding. Let me see here. So this is Monday, Wednesday's class. Let me go to that one real quick. All right, so let's do question 30. Questions. Question 30. Present. Okay, so I'm presenting it, but it's not a big deal. It won't count against you. So name the tacticity. When a specific branch of a polymer repeat unit is always on the same side of the polymer backbone. So repeat unit is a mer. So we're looking at the backbone, and we have side groups that are all on the same side. Is that isotactic, syndiotactic, atactic or cistastic. And I'll give you a hint. D I made up. There is no cistastic, so it's one of the top ones. All right, so when we have all of the side groups on the same side, that's iso. So it'd be A, isotactic. Syndiotactic would be alternating sides in a repeating pattern, and atactic would be alternating sides but randomly alternating. Okay, so the answer to this would be isotactic. All right, so let's go back to this. So copolymers, there's 4 types of copolymers, and basically this would be the attachment of different polymers together. So say the black is polyethylene and the red is polypropylene. So 2 different types of polymers. Polyethylene has the carbon-carbon and hydrogens. Polypropylene has the carbon-carbon, 3 hydrogens, and a methyl group. So I can attach polyethylene to a polypropylene, and if I do it in kind of a random assortment, and I have a few mers here, and I attach them randomly, maybe I have just 1 or 2 mers, and I attach 10 or 15 mers of the other polymer, that would be a random copolymer. Okay. Or if I'm very specific, I could have very specific sizes of polyethylene, polypropylene. I can alternate them back and forth. Okay. So this isn't side groups. This is the actual chain, the actual backbone of the polymer that is alternating between 2 types of mers. Okay. So that would be an alternating polymer. If I take really large chunks of polyethylene, several mers, and then I attach them to really large chunks of polypropylene, that would be a block polymer. So that would have very specific properties as well. Okay. And the last one, actually very common, is a graft polymer. We take 1 long chain polymer, in this case we'll say it's polypropylene, and then at certain spots we knock off the methyl group or the hydrogen group and we attach polyethylene, a big long chain of polyethylene. So we're creating branching. So the main branch would be almost like a branch coming off a tree, and then the tree branches again to create another path. That extra branching would be, say in this case, a block or a graft of polyethylene on the polypropylene original branch. Okay, and we can continue to do that at any point. So that's the 4 types: random, alternating, block, and then grafting. So grafting, you're adding side groups to a chain, whereas the other 2 you are altering the chain itself. Okay. So if we look at that, these are some examples of a lot of the polymers that we'll see. Nice linear polymers, long chains, not much going on with the side groups. This would be kind of like a polyethylene, right? Or then we could take a polyethylene, we could attach side groups to it and start creating branches. And then we'd have other branches near it as well. Okay. Then the next thing would be to actually take the branches and connect them to the adjacent polymer chains. So these chains are floating around, they have a branch connecting the 2. It attaches at both points. Here. This is called cross-linking. So we're taking separate polymer chains, adding side groups to them that actually attach to the next polymer chain up. Okay. And then the most interconnected would be kind of like the Bakelite material. It has that hexagon shape. We have other directions of polymer that can come out and attach to other hexagon shapes. You can do that over and over again. You make kind of a chicken wire or a mesh system. Okay, so let's think about properties of the material. So we have polymers that are very soft and ductile, which means we can pull them and they'll stay stretched out. And we have very hard and brittle materials that are very, like ceramics. So the soft ductile materials are kind of like a metal where we can distort it and it stays distorted, but the strength is obviously much lower than metals. Or we have very stiff, strong polymers that are brittle that act like ceramics. So which one would act like which, right? So we have these long chains that are kind of bound together by just hydrogen attachment, but there's no physical bond between the chains, the backbone. This would be a more soft, ductile or metal-like, I'll say that, polymer. Okay, and as we branch it, it still can slide, but really all we're doing here is this one is I can crystallize. This one is amorphous. So this would be the softest of the materials because it still slides, it's still very ductile. It doesn't have interconnecting bonds to keep it from moving, and I can't crystallize it very well, so its amorphous is typically less strong as well. So this is strong and soft. This one would be weak and soft. And then let's look at the next one. Now we have the branches, but now we're actually attaching them to the other ones. This makes the material very strong, and it reduces ductility, so it starts to make it brittle. Okay, so now when I pull on it, it's these branches that actually are interconnected or cross-linked stop the motion from sliding, so I get a more brittle, stiff, put that too, stiff and brittle material. Okay, and then obviously this last one, very interconnected. If I pull on it, I automatically get resistance. This is the strongest. It's also the most brittle. Okay, so we can have very soft or ductile metal-like polymers, and we can have very hard and brittle ceramic-like polymers. But again, they're not at the same level, but a lot of polymers, some of the newer ones, do have properties very similar to metals and very similar to ceramics. But they also have other properties that are quite useful as well, especially density. Density is a lot lower typically. So that's kind of an interesting, and that it all comes down to the way that they're bonded and the shape of their backbones and the way that they're interconnected with other polymers of the same type. Okay, so let's look at, we were talking about crystallization of polymers, where they fold up into nice rows and columns. This is actually what crystals look like if you looked at them under an electron microscope. You see these layers of crystals that start to form. They kind of layer on top of each other, and they're very organized. And this diamond shape is pretty common for polymers. They like to create this diamond type shape, and they expand outward this way. But they work just like what we talked about with metals. A metal will start to crystallize in one spot when the temperature is just right, and they'll start forming crystals. Same thing with a polymer. There'll be a position that will start, then there'll be another position nearby that'll also start to crystallize. They will grow outward until they hit each other and they form a gap, or kind of a grain, right? The grain boundary between them. The crystals would be the rooms, and the grain boundary would be the hallways in the building, and the building would be the entire polymer. Very similar structure that we talked about before. Just the crystals look different. They don't take these nice, perfect cubic shapes, or take hexagonal shapes, or tetrahedron, or those kind of things. They make these very layered diamond patterns. Okay, but the process is the same. The other issue is it's very hard to make a very highly crystalline polymer. I mean, we have large sections of crystallization in it, but overall it's almost impossible to ever have 100% crystallinity. And this is the reason why. Polymers, the monomers have to form mers that have to repeat to create a polymer chain. In this case, the polymer chain is really short, but the one right next to it is really long. It continues around and goes down here. So this is a huge polymer. So there's two shapes, and we get these within the same material. The reaction went kind of short here for this one, and then the long one created a big one. So the small ones will actually inhibit crystallization, because the long polymers can fold over, make these regions where you have everything nice and layered. Right? So I'm going to circle all of the crystalline regions. So kind of ignore the blue and yellow. It looks like they got shifted in making these slides. So let's just look at my red circles. These would be the crystalline areas. So this is a fairly highly crystalline polymer, but as you can see, there's these huge sections in between that are amorphous. The polymer chains just don't line up very well. So if I were to guess, I would probably guess that these regions in this entire volume, there's probably only about 30% crystalline. Okay, this is enough to make it opaque and to make it pretty strong, but about 70% of it is still amorphous. Okay, so when we talk about percent crystallinity, we talk about what's the maximum crystallinity we can get for each type of polymer, and that will be kind of its 100% crystallinity, and then there'll be a minimum, which is typically 0, where we don't have any crystals. But in this case, 30% might actually be the maximum this polymer can form. So it depends on the material, and that'll be related. Percent crystallinity will be related to the density. Higher crystallinity will be higher density, and we want to adjust crystallinity because it dramatically improves physical properties. It strengthens the polymer, but also makes it less ductile, which we've talked about as well. Okay, so this is what it really looks like. We have a nucleation point, and then the polymer grows outward, crystallizing in these branches, kind of like branches from a tree. So you have the center would be the stalk of the tree, and then you have branches coming off of the stalk going outward, and they go out, and then the space in between is actually amorphous. So right in here, the crystals aren't forming. So if you zoom in on it, look at this one. Here's the stalk of the tree, here's the branches, and the branches start to branch into other branches, and you can see the real crystalline pattern, back and forth, and it branches, continues. But the empty space is amorphous. So this is an amorphous region. So the branches are the crystalline regions, and if this really were a tree is a good example. You have the stalk where the crystallization started. You have the branches that shoot off of the stalk, and then the branches will branch into smaller pieces. And then the whole point of having branches is to be able to grow leaves, which can absorb energy from the sun. The leaves would be the amorphous regions, right? Because they don't have a real structure to them. They just kind of hang off. They're kind of clumped together, and they make the whole material look full. So obviously in the springtime and the early summer, trees look very thick and full because they are a small percentage of branches, but in a large percentage of leaves. So, but in the winter, like now, you look at a tree and it looks pretty sparse because really all that's left is the crystalline structure. So if we were talking about a tree being a polymer, the stalk and the branches would be the crystalline regions, and now all the leaves are gone. You can see that there's a huge section of the polymer that is void of crystalline structures. Therefore, there's a large amorphous region. Okay, so I think a tree, branches, and leaves is a good analogy for crystalline versus amorphous volumes. Okay, so if you look at most polymers under an electron microscope, you'll see the bands of crystalline regions, and the way that the light reflects or the electrons bounce off of polymers makes this cool pattern. Looks like kind of a cross pattern. So this is known as the Maltese cross. This is a well-known design that the Germans used in World War II, good or bad, obviously. But this is a very well-known shape that you see for most polymers. So the crystals form around it, they radiate out, and they reflect the light and create this cross pattern. But you can see these are the hallways or the boundaries between the crystalline formations, and then in between of these rotations would be the amorphous regions. Okay, so this one doesn't have a lot of amorphous regions. This looks like a fairly polymerized or crystallized polymer, and that's because it has the tendency, it must be like a polyethylene, something that's very easy to crystallize. Oh yeah, it does say it's polyethylene. Okay, that makes sense. Cool. So polyethylene you can crystallize to a very high percentage, whereas other ones can be very difficult. Okay, so let's end with the two types of polymers that exist. So we can classify them by their properties and by the branches that we talked about. So if we have a polymer that is branching and they kind of line up together to form crystals, or we have polymers that have branches coming off, then we have polymers that branch but also attach to the adjacent polymers with their branches, and then we have the ones that can cross-link into very tight shapes. Okay, cross-linking. Okay, so these type we talked were very soft and they are ductile. These are thermoplastics. These are ones where there aren't a lot of cross-links. The chains are independent and they line up next to each other and they're held together by secondary bonds, so they're very ductile. What's nice about thermoplastics is you can soften them by heating them. If you heat them enough, they melt. You can cool them and you can reshape them over and over again. So they are recyclable. Usually if you heat and cool polymers too many times, they start to break down. So plastics are recyclable, but usually only 5 to 10 times. And then they degrade and you have to turn them into something else. Okay, so all of our very simple polymer chains, polyethylene, propylene, even polycarbonate, even though it's a complex monomer, the chain doesn't have a lot of weird side groups on it, it's considered a thermoplastic. And that's because it's not cross-linked with other chains. Okay, but if we cross-link it, we get thermosets. Thermosets have lots of cross-linking. So these two in particular would be thermosets. These two would be thermoplastics. Okay, so significant cross-linking, usually 10 to 15% of all of the repeat units are attached to something else. Makes them very hard, also makes them brittle because you can't pull them apart very easily. And they do not soften when you heat them, so they actually burn. Instead of melting, they burn. That can be fairly toxic. So rubber, like rubber tires, epoxies, glues that you mix together and they get hot and then you spread them out and you have a few minutes to maybe attach two things together. The Bakelite we talked about. Resins are another type of epoxy. These are all thermal sets. Once they're set, they stay that way and you can't soften them and reshape them. So the rubber is a good example. Rubber tires, most people know you can't melt those and create new tires. You have to, and you're not allowed to burn them because they release sulfur and a lot of nasty stuff when you burn the polymer. So usually what you do is you reuse. You can't recycle because you can't reshape them. You reuse them. And well, many of you probably know they'll take tires and they can chop them up into chunks. They can color them. They use them a lot on kids' playgrounds to replace wood chips. Kind of soft, you don't get splinters, stuff like that. That is old tires from old cars that they're repurposing the tires. And then in the NFL, football, I'm kind of a big football fan, as you guys probably know from all the stuff I usually have on my tablet about fantasy football. Football uses rubber components all the time in their stadiums in particular, especially on the football fields. So if you have a football field with a artificial turf, that turf is now, since about 10 years ago, the football stadium in Detroit, the Detroit Lions football stadium was the first to do it. They use rubber to create the grass. So the green grass is rubber, and they pelletize the rubber as well, and they kind of spread it out in the grass. Okay, so they can color the grass green, and then they add other pellets in there. The idea is it's supposed to have a softness more similar to natural grass and dirt versus AstroTurf, which was very unforgiving. So if you planted your cleat or your foot, you tried to turn and someone hit you, you would definitely break or tear out your ACL or break your leg or something like that. The new ones are supposed to reduce that. I guess it's hard to really tell because a lot of people get injured all the time in football, but it's supposed to act more like natural grass because the pellets in the grass are shifting, and so when you plant your foot, it should be a little easier for your foot to shift, and you won't hopefully damage your ligaments as easily. It's also used really well for instant replay. Now that the game has gotten faster and everything comes down to inches and millimeters determining whether you're inbounds or out of bounds, the pellets, the vulcanized rubber pellets that they put in the grass, have become a great marker. So if someone, say, throws a pass and catches the ball and they slide out of bounds, or they tap their foot to show that they're in bounds, the little rubber pellets will kind of spray up off of the turf, and you'll see them in the instant replay, and they can verify that that person was, say, in bounds with their catch. So that's become kind of a popular after effect. These little pellets help soften the turf, as well as improve the calling the game from a referee standpoint. Okay, so we'll go ahead and stop there. You need to watch this video by Monday after Thanksgiving, because I'm going to continue on with examples of molecular weights of polymers in Monday's class, and you'll have a homework due soon after that anyway. So yeah, actually I believe, yeah, there is a homework due on Monday, so you'll need to turn that in. And if you watch this beforehand, it will help, because some of the last few problems on the homework are from this lecture. Okay, have a good Thanksgiving, and I'll see you on Monday the 27th.